Okay. Welcome back. We are now in the last part of the pchem crash course. In this lecture, I basically want to take what we developed over the course of the last 3 crash courses, or actually where we kind of got by the end there, and relate that back to what we're doing in kinetics, thinking about how we create rate constants and really frequency factors for molecular level reactions. So basically in the crash course, we took 3 crash courses, about 30 minutes each, and at the end of all of that, we arrived at an expression for the various contributions for entropy of an ideal gas. So there are 3 contributions to entropy: translational entropy, vibrational entropy, and rotational entropy. That's for molecules. If it's an atom, if it's a gas atom such as helium, then you're going to get rid of the you're going to get rid of the vibrational and the rotational contributions to that. That said, since we're dealing with reactions, which is breaking and forming of bonds, we rarely are dealing with only atom systems. So we usually are dealing with systems where the contributions to entropy are going to be translational, vibrational, rotational. Okay, so how does this relate to molecular level reactions? And particularly, we are looking at molecular level catalysis. So how does this relate? Well, one way is adsorption. So if we are thinking about a catalytic reaction, we've drawn this before where we have our reactor level, and we have stuff flowing through there. But if we kind of took, just a piece of that and we blew it up, we have catalyst pellets within there. And if we took one of those catalyst pellets and blew that up, we have this porous thing. So pore structure, it's a spherical particle, but it's got lots of pores, making the analogy kind of like this is kind of like a sponge. So if we looked at one of these pores, what we get is something that looks kind of like this, and this is, of course, no pore looks exactly like this. I'm just kind of drawing something. Maybe it's closed at some point. It doesn't have to be closed, but I'm just giving an example. And then if we said, okay, let's zoom in even further and look at the surface of this thing. So here's the surface of the pore. Then I might have on there a catalyst particle. So here is metal oxide support, and here is a metal catalyst particle. And that's kind of dispersed along the surface area of this pore. And then I could zoom in even further. So the catalysis is going on maybe here. And so now I have this metal catalyst surface. And I have molecules, gas molecules. So carbon monoxide, for example. And that carbon monoxide is attempting to adsorb to the surface. So now let's back out of all of that. Come back over here. Adsorption is going to happen when I have molecules, and let's say I can continue to have carbon monoxide, but I'm going to approximate carbon monoxide as a sphere. So I have gas molecules, and they're whizzing around. And maybe I have one that is going to collide with the surface, and as it does so, it forms a bond with the surface. And maybe some others have done that before. So what I basically have are 2 phases here. I have one, my ideal gas. These have 3 degrees of translational freedom. They have full, we'll just say full rotational and vibrational freedom. And now that we have gone through the pchem crash course, we know what we mean by that. So it has the full rotational mobility based on the moments of inertia in the molecule. It has full vibrational mobility based on the different bonds within the molecule and the different degrees of freedom. Our second phase is going to be this adsorbed phase. There are various ways to model this. I'm going to give you the simplest one, and just trust me that that this works for what we want to do, but if you go and study this field, you're going to have to make a lot of decisions about the types of models and assumptions you make. But we're going to assume that these molecules have 2 degrees of translational freedom. So these molecules are constrained to the surface, so they can't leave the surface. So now they can only zoom around on the surface, right? So the gas molecules are everywhere. The adsorbed molecules are anywhere on the 2-dimensional lateral surface. So they only have 2 degrees of translational freedom. They have restricted, well, actually, let's say these molecules have no rotational freedom. That is a approximation, but if you're stuck to the surface, you probably can't rotate. It's actually called a hindered rotor, but we can assume that they have 0. And now they honestly have new vibrational degrees of freedom. The reason they have new vibrational degrees of freedom is because they formed a new bond. So some of the vibrational modes are going to be similar. So you're still going to have that CO stretch. It's still stretching even though it's bound to the surface. That's going to be altered because of the new bonds it's formed. But it's also going to have all sorts of new vibrational degrees of freedom because it formed this new bond on the surface. So thankfully, when we're thinking about entropy, the translational contribution is a lot larger than the vibrational and rotational, so we can reasonably approximate changes in entropy of a molecule due to adsorption based only on its translational entropy. And we can kind of hand wave the change in the rotational and vibrational contributions. We can kind of say that it's going to be equal to 0. It's not 0. We know it's not 0, but those contributions are much smaller than the translational contribution anyways, so let's just not worry about them because they're also more complicated. Okay, so let's talk about the translational piece. So the translational partition function for a 2-dimensional gas, which we could derive in the same way as whoever derived it for us for the 3D gas did. So I'm not going to do that derivation, I'm just going to write it down. The translational partition function for a 2D gas is this function here. You'll see it's quite close to that for a 3-dimensional gas, but it's to the 1 power, the first power instead of the 3/2, and then also it's multiplied by area instead of volume, and we get there through all of the same steps as we took to get to the 3D gas. So this would be for the translational partition function for a ideal gas atom that is adsorbed to a square featureless surface. Okay, so we know from the last lecture that we can use this partition function to estimate the entropy. That's going to be the Boltzmann constant times the natural log of the partition function. The entropy associated with adsorption, so that's going to be binding of an ideal gas to a 2D surface, so that would say delta S adds, is then going to be equal to S2D, and let me say S trans 2D, so translational in 2D minus translational in 3D, and that's because adsorption is your, for example, carbon monoxide gas molecule reacting with a catalyst site to form adsorptio. So this is your 3D translator. We'll say this is your ideal gas. And this is your ideal gas, now constrained to a 2D surface. So if I want to take the entropy of that process, I take the entropy of the products minus the entropy of the reactants. That's going to give me my 2D translator minus my 3D translator. Okay, so basically then, if I want to do that, I would say I'm going to take KB natural log Q trans 2D minus KB natural log Q trans 3D, but these are natural logs, so by subtracting them, I can also divide them. So that's what I've done here, is kind of combine those, and then also fill in those two partition functions. So this is just two algebra steps further than this. Okay, so now I can start to simplify. Since these things look kind of alike, I can start to simplify them out. If I do that, I get that the change in entropy of adsorption of this ideal gas molecule is this expression. Basically what I've done here is I have basically canceled. So I have these two things being multiplied by each other, and I basically did some cancellation there. Now I have this piece that I need to deal with. This is a ideal gas. So this piece comes from the 3D translator, which is an ideal gas molecule. Hence I can use the ideal gas law. So I'm going to do that. This right here is the ideal gas law. So for ideal gas molecule, so this uses Kb, so remember that Kb is equal to the gas constant divided by Avogadro's number. So basically what that gives us is the gas constant on a per molecule basis instead of a per mole basis. So the molecule here, or the unit of molecules here, is implied. So I can sub that in for my volume quantity. This allows me to write in terms of pressure, which is more easy it's an easier observable quantity, or it's an easier set quantity. And so if I do that, then I get an expression for the change in entropy of adsorption based now on all things that I know. This is going to be either constants, or the things I would need to fill in would be the mass of my gas phase molecule, the area, which is the area of the surface, and also the pressure. Okay, so one of the places we're going is, or maybe we've been there depending on when you're watching this video, that the frequency factor for adsorption can be approximated as this quantity. So when we talk about the frequency factor or pre-exponential term, this comes from the rate constant, is going to be equal to a frequency factor times the exponential of exponential of the activation energy divided by RT. Here we are looking, so how do we calculate this piece? One way we can do that is to take KB times T divided by H times the exponential of the change in entropy of the process divided by KB. And we'll that's shown, why we can do that is shown in the lecture on frequency factors. Okay, so if we do that, then that's going to mean that the frequency factor for adsorption is equal to kBt over h times the exponential of, I'm going to give myself a lot of room here, of kb natural log h over square root 2 pi m kbt ap over kbt all over kb. So what that allows us to do is get rid of that and get rid of that. Once we do that, now we're taking the exponential of a log. So that's going to basically bring everything outside here. 2 pi m kbt, and then we have a p kbt. That goes away. Oops, let me do that in a different color. That goes away, that goes away, that goes away, that goes away. So hence, A adds is going to be equal to the pressure times the surface area divided by 2 pi m kbt. For adsorption, we consider A adds on a per site, so per catalyst site basis. For a metal catalyst, the common value of 1.5 times 10 to the 19 sites per centimeter squared is often used. And for some reason, this is denoted L. So notice here that the area piece is in the bottom. If we do this, we would say A adds is equal to P divided by this L quantity. That puts my area back in the numerator where it needs to be, 2 pi m kbt. And so that is the frequency factor for adsorption. Also equal to, if we would arrive at this exact same quantity if we just wrote a model for an ideal gas and calculated the flux of ideal gas molecules to a two-dimensional featureless surface. And that's it. That's all we need to do. Now we can get back into frequency factors.